So today we're going to talk about quantum chemistry, and we'll start by refreshing our memory on energy, specifically the units of energy. So let's get right to it. As you may remember from the thermodynamics lecture, the total amount of energy of any system is really the combination of kinetic energy and potential energy. And specifically, we talked about heat as being the source of the kinetic energy. We talked about the molecular theory of gases and how heat is ultimately correlated with the temperature of the gas. And the potential energy itself is the work performed by the system or done onto the system, based in our case on pressure volume changes. You may remember also that I mentioned that roughly speaking, the heat of a substance can be approximated by the temperature of the substance itself. And here I'm presenting, not that we're going to be using this constant, but I'm presenting the Boltzmann constant, which basically allows you to calculate the amount of energy heat that a gas particle has based on a single gas particle being present. So this is actually a very tiny number, as you can see, 10 to the negative 23. But the heat itself ends up being joules once you do this conversion. Now the same type of analysis we also looked at in terms of the gas constant, 8.3145, multiplied by the temperature. Roughly speaking, that gives you an idea of the amount of energy in the form of heat that a system possesses. So this is nothing more than just restating the fact that heat is a measure of temperature itself, right? And this is kind of approximate. It does depend on the specifics of the system itself. But the main idea is that the heat is given in joules or joules per mole. Then the work, in the physical traditional sense, work is force times distance. And force itself, via the second Newtonian law, is simply mass times acceleration. So we have mass times acceleration times distance providing the work, so, and kind of like they say, all work and no play makes Alex a mad boy. Yeah, so that's kind of what we have right here. But in terms of looking at the units, the mass is in kilograms, the acceleration of a substance is in meters per second squared, and the distance is in meters. So you end up generating units of kilogram meter squared over second squared, which we stated previously is nothing more than the joule, right? So the joule is just a collection of units. And this is more of a reminder for what we're going to be doing, because we're going to continue with this idea of energy in joules. And in some instances, we will actually revert back to thinking of joules in terms of kilograms meter squared over second squared. Okay, but that's kind of what I want to remind you of in terms of energy. Let's talk a little bit about waves, and what are the main things you need to know about them. As it turns out, quantum chemistry is technically all about waves, as you're going to find out. So first, let's talk about the essentials of waves. All right, so here we have a wave. This could be, and it looks to be, a sine wave if you start right at the left point as being the origin. And pretty much a wave is a pattern that repeats itself, an oscillation, if you will, whereby an actual wave goes through crests, the upper portions of the wave, and troughs, the bottom portions of the wave. And this pattern repeats itself over and over. You might recall seeing this in algebra or maybe in trigonometry classes in the past, where you basically look at the distance of the wave going up and down in the y-axis, the distance as the wave propagates to the right as the x direction. And you might even remember that the particular portions of the wave, if this is the sine wave, can be attributed to particular distances in radians, right? So the crests happen every pi over 2 plus 2 pi, right? So we have pi over 2, 5 pi over 2, 9 pi over 2 for the crests. The troughs happen exactly at an additional unit of pi, so 3 pi over 2, 7 pi over 2, etc. And then there are some points that do occur right where right the x-axis, meaning that there is zero amplitude at that particular place. So that happens at pi, 2 pi, 3 pi, 4 pi. So you might remember this from your trigonometry days. Now, the part about this is kind of important. I'm just going to highlight it. I'm not going to test you on trigonometry in this class. Not to say that we won't use some of the characteristics of trigonometry to explain certain details, but this is just to give you an idea of where we're going with it. All right, so looking at the pattern of oscillation of the wave, you might notice that by the time we go through a crest, pass through a trough, and go back to the origin, we have completed an entire cycle of the oscillation. And it so happens that that cycle is completed exactly at 2 pi. And the time that it takes the wave to complete the oscillation is what we call the period, right? So however long that takes to complete that cycle, that is the period of the wave. You may also remember that when it comes down to waves, this actually has a different graphical representation, one of a circle. Specifically, the values as the wave propagates on the x direction are actually the angles as we go around a circle. And we have basically 4 quadrants in the circle. We have 0, 2 pi, representing the initial and final point of the full oscillation. We go through pi over 2, pi, and 3 pi over 2. And this basically completes an entire oscillation for the wave. And then we start looking at the intermediate points, like specifically the half points, the pi over 4s, 3 pi's over 4, 5 pi's over 4, 7 pi over 4s. They happen exactly midway between the origin, the x-axis, and the crest or trough of the wave. And those are basically the midpoints also on your unit circle. You may also remember your pi's over 6, which are closer to the x-axis. Those are also, the ones that are closer to the extremes of the waves, right? They're farther to the left or farther to the right. And then you have your, pi's over 3s, which are closer to the middle of the waves. They are actually closer to the pi over 2 vertical axis. So this is just a reminder, nothing more than that. But the interesting thing about this is that, technically speaking, what tends to be easier for us in terms of calculating the period is not to see how long it takes for one oscillation to be complete, but rather to measure a unit of time, like let's say 10 seconds. And within those 10 seconds, you see how many times the wave goes through this oscillation. So if you divide the time by the number of oscillations in the version of 2 pi, which is basically how long it takes for this wave to go through the oscillation, you basically get the period of the wave. A better way, though, to think of this is kind of the opposite, via something we call the frequency. And I'm using the letter F to represent frequency, although in a little bit longer, in a different video, you'll see me use the Greek letter mu. But the frequency is basically, in essence, the opposite of the period. It's the number of cycles of oscillations that you go through in some amount of time, usually in seconds. So you count how many cycles you go through, let's say in 10 seconds, divide that number by 10, and you get your frequency. And as I said, the frequency is directly the inverse of the period of the wave. All right, the other aspect of a wave that's going to be of importance to us is what usually gets described as the distance from crest to crest of your wave. That distance is what we call the wavelength, right? And kind of like the name implies, we're looking at the length that it goes to go from one wave to another. The wavelength has also a specific Greek letter that goes with it. This is called lambda, and lambda just represents the wavelength. Now, what I need you to notice is specifically where the crests land on each one of these points where we're measuring the wavelength. The first one starts at pi over 2, the last one ends at 5 pi over 2. And if we look at the difference, 5 pi over 2 minus pi over 2 is the same thing as saying 4 pi over 2. But 4 pi over 2 is also the same thing as saying 2 pi. And the interesting thing about this is that it turns out that the entire oscillation of a wave is exactly equal to the wavelength of the wave. And that has some crucial consequences for how you can start writing equations for waves that kind of allow you to go from the wavelength of, or actually to use the wavelength of the equation to correlate to the distance of propagation of the wave. Now, speaking of distance, um, since the wavelength is pretty much measuring that, technically the distance from crest to crest of the wave, which we just found out to be equal to 2 pi. Now 2 pi in essence is a representation of the angle associated with the wave. So you could say that based on this premise, the wavelength is equal to 2 pi, which is the distance. And this kind of allows you a conversion factor to introduce into trigonometric functions like the sine wave or the cosine wave. Specifically, if you want to get the angle associated with the process in terms of the wavelength, well, as long as you measure the distance by which the wave has traveled, you divide that by the wavelength and multiply by 2 pi, and this allows you to basically end up with an angle value for your wave. So this is something important for quantum mechanics, quantum physics. This is more for your information. I'm not going to actually be testing you on this equation, but I want you kind of to be aware of the fact that wavelength can be used as a conversion factor to go from length back to units of angles. Now, the one thing that I will test you on is this, the speed of the wave. As depicted, the frequency is 1 over time, right? 1 over the period. So we have 1 over time, or seconds to the negative 1. Oftentimes we refer to seconds to the negative 1 as hertz. Those two units are the same thing. They're synonyms. And we have the wavelength, which is in units of distance. Let's call it the meter. If we basically multiply the frequency with the wavelength, what we're going to end up with is finding out the speed of the wave, because we have mass times 1 over second, which is meters per second. All right, we're almost there. Now, the last part about waves that you need to be aware of, which is going to be more important for the upcoming lecture, is the fact that when you have waves of the same pattern, right, so the crest meets with crests, they actually add up with higher amplitude. But when they actually meet out of phase, meaning that the trough of one wave meets with the crest of another, they completely cancel out, and this is known as destructive interference. All right, this is where we're going to stop the first video. These are all the essentials that you need to know, but now we're going to get a little bit more in detail. So see you on the next video.